Okay, let's dive into this. Welcome, educators. Today, we are tackling one of the absolute most persistent, fundamental challenges in education. Right? How exactly do we move students beyond simple, rote computation and into the realm of genuine mathematical reasoning? Well, in this explainer, we're going to explore how we can use Bloom's taxonomy, specifically tailored for the math classroom, and discover a real game changer of a toolkit that can dramatically elevate the dialogue and the thinking in your daily lessons. Here is our roadmap for today. We'll start with part 1, beyond rote computation, move to 2, the 3 math domains, then 3, climbing the base, 4, reaching the apex, and finally, part 5, classroom implementation. We're going all the way from the foundational history straight to actionable strategies you can use tomorrow. Section 1, beyond rote computation, the mathematical shift. So, for a really long time, the overarching goal in math was just producing the right answers quickly. But we know we need students to actually think, analyze, and reason like true mathematicians, not just act as human calculators. Think about the standard prompt we see literally everywhere. Solve the problem. Now compare that to a Bloom's enriched prompt. Which solution strategy is most efficient? Justify. The leap in cognitive demand there is massive. We aren't just asking what's the answer anymore. We are actively challenging the student to explain why is this the absolute best way to find it. To truly appreciate this tool, it kind of helps to briefly trace its enduring legacy. Between 1949 and 1953, a committee of educators held a series of conferences just to create a shared language for educational objectives. And this culminated in 1956 with a publication of what was simply known as the Handbook by Benjamin Bloom. It is crazy to think about, but a framework older than the microchip is still incredibly relevant today. This 1956 shared language maps perfectly to the cognitive demand of modern adaptive assessments, like the NWEA MAP RIT, mirroring how standardized testing increasingly challenges our students' thinking. Section 2, the 3 math domains. Now, it's absolutely crucial to understand that true mathematical mastery requires a whole student approach. Let's officially define what we're talking about here. Bloom's taxonomy is a framework classifying learning objectives into 3 distinct domains: cognitive, affective, and psychomotor, all designed to elevate educational design. And the word taxonomy is key here. It's not just a list, it is a hierarchy. Higher levels of learning will always depend on mastering the foundational levels right below them. Let's break those 3 domains down into how they actually look in practice. Domain 1 is the cognitive domain, or the head. This involves mental skills and reasoning, everything from recalling your times tables to synthesizing complex proofs. Domain 2 is the affective domain, the heart. This is a student's math identity, their persistence, their growth mindset. And domain 3 is psychomotor, the hands. These are the physical actions, like the precise fine motor coordination needed to use a compass, a ruler, or a graphing calculator. Now, all 3 of these domains are working simultaneously during a great math lesson. But for the rest of our time together, let's focus our ascent specifically on that first one, the cognitive domain. Section 3, climbing the cognitive pyramid, building the base. We're going to use a laddering metaphor to start our literal ascent up the cognitive pyramid, beginning with those vital foundational levels. Let's look at the first 3. We start at level 1, knowing. This is all about clarifying and recalling information. You might use an example stem like list all factors of Planck. Moving up to level 2, we have organizing. Here, students are arranging and comparing, answering prompts like sort these numbers from least to greatest. Then we reach level 3, applying. This is where students use prior knowledge to solve a new problem, such as use the formula to calculate blank. Look, these levels are the absolute bedrock of math instruction. They intentionally activate prior knowledge so students actually have the raw materials required to solve complex problems later on. Section 4, climbing the cognitive pyramid, the ascent. Okay, this is the exciting part where genuine mathematical reasoning really takes flight. Let's see how this builds across the next 3 levels. At level 4, analyzing, we start examining parts and relationships. You're asking things like, what rule explains this pattern? At level 5, generating, students are producing new information. You might ask them, predict what happens when, blank. And at level 6, integrating, students are combining and restructuring ideas. A fantastic stem here is, how does this concept apply to a new situation? And this brilliantly illustrates the cognitive shift happening here. Students are no longer just identifying patterns. They're actively creating, predicting, and connecting new mathematical information to build a deep, deep web of understanding. Section 5, reaching the apex. We are building our momentum to the absolute highest point of the cognitive pyramid, level 7, evaluating. Consider this Level 7 question. Which solution strategy is most efficient? Justify. It carries a lot of weight, doesn't it? This apex level is all about judging reasonableness, confirming accuracy, and rigorously defending choices. When a student can answer this, they aren't just doing math anymore. They are evaluating the mathematical process itself. This is the ultimate goal. Section 6. Classroom Implementation Strategies. So, what does this all mean for you on a random Tuesday morning? How do we make this a reality? Let's transition from theory into action and weave these concepts into your daily routines. It all begins by building a math dialogue culture, framing questions with sentence frames like, who agrees, disagrees, who will explain why or why not, creates an environment where students expect to justify their thinking and safely challenge each other's reasoning. They learn to build on peer responses rather than just sitting around waiting for the teacher to validate an answer. Next, we have a fantastic strategy called ladder your questions. You can literally ladder your questions to effectively sequence a single class period. Step 1, open your lesson with a level 1 or 2 STEM. Get them comfortable, activate that prior knowledge. Step 2, climb the pyramid as the lesson progresses, moving into application and analysis. And step 3, always end with a level 5 to 7 STEM. Make sure the final thought of the lesson pushes them into genuine higher order reasoning. Let's rapid fire through a few more highly practical tips. First up, try rotating question word walls quarterly to match students' NWEA MAP RIT growth targets as they improve throughout the year. Second, don't just speak these stems, put them in math journals and on exit tickets for much richer writing prompts. Third, explicitly pair these higher order stems with the 8 math practices, specifically things like SMP3 and 6, which are all about constructing arguments and attending to precision. Finally, if your school uses other questioning frameworks like COST as levels 1 through 3, know that they integrate beautifully and serve as a perfect companion to Bloom's. I want to leave you with this provocative final thought. If your students can easily compute the answer, but they cannot defend the strategy they used to get there, have they truly mastered the math? Take these Bloom's question stems, implement them into your daily dialogue, and watch your classroom completely transform from a room of calculators into a vibrant community of true mathematical thinkers.